Hi everyone, hope you are doing good. This is Mageshwari. I am from Department of SNH Mathematics. Today we are going to see about the topic is double integrals. In the chapter, we extend the idea of a definite integral to double integrals of functions of two variables. These ideas are then used to compute volumes, masses of more general regions. Then we were able to consider this session. So there are two contents is there. First one is introduction to double integral. The second one is evaluation of double integrals. So in this section we will learn about double integral and using them to find the volumes and average values just as our attempt to solve the area problems. In this process we arrive at the definition of a double integral. So first let us recall the basic facts concerning definite integral of functions of a single variable. So see the definite line integral definition. So integral a to b f of x into dx. This is called a definite line integral. See the next definition, double integral. So we integrate a function f of x comma y called integrand over a closed bounded region or in the xy plane, whose boundary curve has a unique tangent at each point but may have finitely many curves such as varieties of a triangle or rectangle. So see the diagram. So we consider the xy plane. So the domain is D. For double integrals, we want to be able to integrate a function f not just over rectangles but also over region domain of more general shape. So we suppose that D is a bounded region. So see the diagram. This means that D can be enclosed in a rectangle region or as shown. Therefore, we define a new function f with domain R by f of x comma y equal to f of x comma y if x comma y is in the domain, 0 if x comma y is in the R but not in the domain. If f is integrable over R, then we define the double integral of f over the domain by double integral the domain f of x comma y domain of a equal to double integral or f of x comma y d of a, where f is given by the equation number 1. So definition 2 makes the sense because R is a rectangle and so double integral or f of x comma y d of a has been previously defined. The procedure that we have used is reasonable because the values of f of x comma y are 0 when x comma y lies outside the domain and so they contribute nothing to the integral. This means that it does not matter what rectangle or we use as long as it contains the domain. So in particular this is the case for type 1 and type 2 regions. So first see that type 1 region. A plane region D is said to be of type 1 if it lies between the graphs of two continuous functions of x, that is domain x comma y, x is lies between a to b and y is lies between the function of x g1 of x to g2 of x, where g1 and g2 are continuous on closed interval a comma b. So some example of type 1 region are shown. The first one is region in xy plane as bounded above and below by two function of x. So y is a function of x in these two cases. X is bounded by inner where the x axis y. So see the third diagram. You can see the different cases. The two curves y equal to g2 of x and y equal to g1 of x meet the endpoints. And see the second diagram. X comma y is such that x is lies between a and b in y depends on the x. Here lies between two function in the two curves. That means in this case one curve in the breaking up top portion and bottom portions. Therefore, integral c to d f of x comma y dy equal to integral g1 of x to g2 of x f of x comma y into dy. This is equal to g1 of x to g2 of x f of x comma y into dy. So because f of x comma y equal to f of x comma y. So where y is lies between g1 of x to g2 of x. Therefore, if f is continuous on the type 1 region, therefore domain x comma y such that x is lies between a to b and y is lies between the function of x g1 of x to g2 of x. Therefore, double integral the domain f of x comma y d of a equal to double integral a to b gn of x to g2 of x f of x comma y dy into dx. So therefore, the integral on the right side of the previous equation is an integrate integral that is similar on the ones we consider in this session. So see the type 2 region. See, we also they consider planned region of type 2, which can be expressed as domain equal to x comma y. Y is lies between C2D and x is lies between h1 of y to h2 of y, where h1 and h2 are continuous. Using a similar arguments as for type 2 regions, we can show that integrating a function over a type 2 region can be done as follows. Double integral the domain f of x comma y d of a equal to integral c to d integral h1 of y to h2 of y f of x comma y into dx into dy, where the domain is a type 2 region. So therefore, type 1 and type 2 region as follows. For type 1 region is known, you first integrate of y first. For type 2 region is known, integrate x first. It is clear. So note the points. For a type 2 region, the arrow is drawn horizontally from the left boundary to the right boundary. So for type 2 region, type 1 region, the arrow is drawn vertically from the left boundary to right boundary. It's clear. Next, see the problems based on type 1 region. So find the values of the solid that lies under the parabolized z equal to x square plus y square and the above region domain in the xy plane bounded by the line y equal to 2x and the parabola y equal to x square. So we consider the xy plane. You draw a line y equal to 2x in straight line passing through the origin. Then you draw the parabola, so y equal to x square. So first we find the point of intersection, getting the points 2, 4 at the origin 0, 0. So now we want to find the limits of y. So y varies from x square to 2x and x varies from 0 to 2. Therefore, double integral 0 to 2 x square to 2x x square plus y square into dy into dx. So in this equation, the inner integral is y square. So first we have to integrate with respect to y, then we have to integrate with respect to x. Therefore, integral 0 to 2 x square y plus y cube by 3 into apply the limits y equal to x square to y equal to 2x into dx. So therefore, integral 0 to 2 x square 2x plus 2x whole cube divided by 3 minus x square into x square minus x square the whole cube divided by 3 into dx. So simplify the above equation, getting the final result is 216 divided by 35. Hence the solution. See the type 2 region problem. From this figure, we see that the domain can also be written as a type 2 region. So we consider the xy plane. Here we draw or finding the limits for x. So we draw a horizontal strip from x equal to y by 2 to x equal to root y. So that means x varies from y by 2 to root y and y varies from the limits is 0 to 4. So the domain x comma y, y is lies between 0 to 4 and x is lies between 1 by 2 y to root y. Therefore, so apply the result. Therefore, v equal to double integral the domain x square plus y square into d of a equal to integral 0 to 4 integral 1 by 2 to root y x square plus y square into dx dy. So in this problem, so inner integral x is here. Therefore, first we have to integrate with respect to x, then we have to integrate with respect to y. Okay. So therefore, integral 0 to y. So first we have to integrate with respect to x. So x cube by 3 plus y square by x is comes. So close the bracket. So apply the intervals x equal to 1 by 2 to x equal to root y into dy. So integral 0 to 4. If you substituted upper limit and lower limit on the above equation. So therefore 2 by 15 into y power 5 by 2 plus 2 by 7 into y by 7 by 2 minus 13 by 96 into y power 4. So close the interval. So apply the limit 0 to 4. Therefore, if you substituted upper limit lower limit on the above equation, so getting the final result is 216 divided by 35. So hence the solution. Thank you for listening. Thank you for all.